Hi, everyone. Thank you so much for joining us for this webinar. We'll get started in just a moment. Thank you. Hi, everyone. Thank you again for joining us for Seamless Transition to PCI 5.0 Technology and System Implementations as part of the PCI SIG Educational Webinar Series. We wanted to take a minute here to introduce our two presenters today. So we have Casey Morrison, who's the VP of Products at Astera Labs, and then Jonathan Bender, who is the Head of Product Applications at Astera Labs. And I'll go ahead and pass it off to them.
All right, thank you, Megan. This is Casey speaking. Hello, everyone. Thank you for joining this webinar. Today, we're going to be presenting on a few topics about transitioning from PCIe 5.0 to, from 4.0 to 5.0. We'll cover some of the basics of the specification itself, the unique aspects of 5.0 technology, look at some of the signal integrity and link integrity challenges that are somewhat unique and pronounced in 5.0. We'll look at the clocking considerations and clock topologies, and then conclude with some notes on compliance and interop testing as people ramp up to design and implement and deploy 5.0 technology in their systems. So first, in terms of the specification, everyone's familiar with this chart. Basically, 5.0 was released in about 2 years' time after 4.0, so it was worked on very rapidly and released to essentially double the data rate compared to 4.0. PCI Express Gen 5 operates at 32 gigatransfers per second, and with up to 16 lanes that allows for a total link throughput of 64 gigabytes per second. It's worth noting that the PCI SIG is actively pushing towards a 6.0 release, again with about a 2-year turnaround time, sometime in 2021. And with PCI Express 6.0, the data rate will again double to 64 gigatransfers per second. So the PCI SIG continues to improve the PCI Express technology, largely due to the high demand for this unique type of interface. Okay, so in terms of specific parameters that are outlined in the PCI Express base specification, this table summarizes a few of those. Of course, Gen 5, just like Gen 4 and below, uses non-return to zero signaling. This is 2 voltage levels per unit interval. And also the maximum bit error rate has remained the same at 10 to the minus 12. Now, one improvement from Gen 4 is and Gen 3 as well, is the increase in the end-to-end loss budget, which has gone up to 36 dB compared to 28 dB for Gen 4. So it's a very advanced technology. In fact, it's the fastest non-return to zero standard in the industry. And with a 36 dB loss budget, it's a very advanced and challenging technology to implement in the system that provides many benefits for the system. If we look at the transmitter, not much has changed with regard to the transmitter characteristics. the voltage, output voltage has stayed the same between 800 and 1300 millivolts, as has the maximum boost ratio, which is basically the equalization capability of the transmitter. Now on the receiver side, there is this concept of a behavioral model, which is used largely for channel compliance, and we'll look at channel compliance later on. But the behavioral model for Gen 5 has become more advanced, you could say. The CTLE has gone to a second order CTLE. The peaking frequency has shifted higher accordingly, and the maximum boost has increased from 12 dB to 15 dB. And in addition, a third DFE tap was added to the reference receiver to help compensate for some of the reflection characteristics which may exist in PCI Express channels. So again, specific silicon implementations may have a different receiver architecture, but these parameters describe the reference receiver, which is used for channel compliance. One new thing to PCI Express 5 is the concept of precoding. And if we look at a receiver and how a receiver recovers the signal, one common circuit used in a receiver is a decision feedback equalizer. This is a type of equalization circuit which utilizes past decisions in order to influence current decisions. Essentially, you're using the ones and zeros, the decisions that you've made in the past, and some weighted sum of those decisions to help equalize the intersymbol interference, which may be distorting your current signal. Now, that's very helpful for recovering the signal and equalizing effects such as reflections and things like that without amplifying crosstalk. But one potential problem with that is that if the DFE makes a wrong decision, then that wrong decision will be fed back and scaled by a certain weight when making the decision on the current bit. And so that the weight that is used to scale that previous decision, if that's large, then the wrong decision will have a significant negative impact on the ability to make the correct decision for the current bit. And this is a concept known as error propagation, where a previous wrong decision leads to further wrong decisions. Another term for this is burst errors, where you would make potentially one error, and then that one error would cause subsequent errors, subsequent multiple errors that could significantly impact link performance. So what the PCI SIG did was for Gen 5, they introduced this circuit called precoding, which is basically an XOR operation on the transmit data and a sort of a reverse XOR operation on the received data. Now, this does not affect the actual signal characteristics. It doesn't affect the signal integrity. It's more of an encoding and decoding operation, which will help to eliminate or greatly reduce the likelihood of these kinds of burst errors. So it's also important to note that every receiver in the system has the ability to request precoding during link training itself. So every transmitter must be able to implement precoding, and then it's up to the receiver to request that link partner transmitter to either enable or disable precoding for the receiver's benefit. And one final note on this concept of precoding: while it does eliminate burst errors, which can cause significant problems, it does have the side effect of increasing your baseline bit error rate by a factor of 2. And that just has to do with how the circuit works, or how the mathematical operation works, where a single bit error gets converted, or I should say a burst error gets converted into an entry error and an exit error. Okay, moving on to signal integrity and link integrity challenges unique to Gen 5. If we look at the different topologies, system topologies, there are many different kinds of topologies for PCI Express. You can think of servers and storage boxes and GPU trays and things like that. And you'll end up with physical channels that have different characteristics: one connector, two connectors, multiple connectors, cables, etc. So there's no single topology. There's a plethora of topologies, and all of them must comply with the channel requirements, which essentially means they must be less than 36 dB loss at 16 gigahertz. And as every system designer is well aware, the passive components in your channel, PCB, connector, cables, the loss of those components will vary over temperature and humidity effects. And so those variations in loss need to be taken into account when designing the topology and determining whether that topology will meet the 36 dB loss requirement over all conditions, over worst case conditions. And of course, in some more complex topologies involving multiple connectors, physically long channels, some form of a reach extension device or reach extension approach will be necessary, and we'll talk about the different ways of achieving that. Focusing more on the channel loss budget and breaking that down a little bit, this table shows the different components of that loss budget. Of course, for Gen 5, the Nyquist frequency is 16 gigahertz, which essentially means that the frequency response of your channel needs to be well behaved between DC and at least 16 gigahertz. Ideally, it should be well behaved beyond 16 gigahertz, but that's kind of the frequency range that we're dealing with. A 36 dB loss budget has different components to it. The root complex package has been allocated 9 dB of that budget. That sounds like a lot, but if you look at the size of root complexes, they tend to be large. They tend to be situated in sockets. And so there's a lot of signal integrity challenges with root complexes, which justify that 9 dB budget. Non-root port packages, such as endpoints or even retimers, are allocated 4 dB. And then if you were to subtract that from the 36 dB budget, you basically have 23 dB left over for the passive interconnect between the root port and the non-root port, the endpoint. Now, for some standard form factors, like the card electromechanical chem add-in card, those form factors have budgets as well. And for example, the add-in card budget is 9.5 dB, which of course consists of the add-in card PCB as well as the endpoint package. And the connector itself is allocated 1.5 dB. So if you're dealing with an add-in card topology, that would leave a remainder of your budget of 16 dB between the root port pads on your PCB and the add-in card connector. So that's basically what many system designers are working with, is a 16 dB budget to design all the traces, vias, capacitors, etc. Now, one exercise that every system designer needs to go through is determining if their 5.0 channels are compliant to the 5.0 specification. And the standard methodology for doing this, proposed by the PCI SIG, is using a statistical simulator, specifically a tool called CSIM, to simulate the S parameter of your channel and gauge whether it's compliant or not compliant. Now, it's important to note that CSIM implements a reference transmitter and a reference receiver. It does not implement any vendor-specific or silicon-specific transmitter or receiver architecture. So that's good in the sense that it's a common tool used by, I would say, all system designers, and the inputs to that tool are essentially just your S parameter for your system. The other inputs governing the reference transmitter and reference receiver are essentially a template provided by the PCI SIG. Now, to highlight the importance of running channel compliance, we have 3 examples here. On the left, we have a 36 dB loss at 16 gigahertz channel, which has smooth loss characteristics. There aren't any reflections or ripples in the insertion loss. And as you would expect, when you run this through CSIM, it produces what I would call a barely failing, barely passing result. The I height is below the 15 millivolt requirement, but the I width is above the 0.3 UI requirement. So it's on the borderline, which you would expect from a maximum loss channel. Now, if you take another channel in the middle, which only has 33 dB loss at Nyquist, except this channel also has some reflections, some disturbances in the insertion loss profile. Interestingly, this channel has a much smaller I. It fails both on the height and the width requirement, even though it has 3 dB less loss at the Nyquist frequency. So this highlights the importance of running CSIM and not just simply looking at the loss at the Nyquist frequency. And then to kind of round that out, we have another 33 dB channel on the right, which has smooth loss characteristics, and that has a very wide open I, meeting both the height and the width requirement. So not every 33 dB channel is created equal. One of the most important parameters that a system designer will examine when designing a system is the loss characteristics of their passive interconnect. And primarily, this would be printed circuit board material or connectors or cables and things like that. Now, a lot of discussion exists around terms like mid-loss, low-loss, and ultra-low loss PCB material. These are not industry standard definitions, and every PCB material will be different depending on its properties and stack up and things like that. So system designers will look at all of those parameters, and more importantly, they will look at the degradation in loss characteristics of their specific PCB material over conditions like temperature and humidity. In this table we have here, we're showing some examples of common materials which would generally be considered mid-loss, low-loss, and ultra-low loss. And we're also showing the degradation of going from nominal conditions to worst-case conditions. And you can see that the insertion loss may degrade by between 8 and 16%, depending on the material properties. Also, the type of routing, whether it's strip line in a buried layer or microstrip on the surface layer, affects the insertion loss per inch, with microstrip having higher loss per inch. So if we kind of stand back and look at this table and maybe zoom in on the 16 gigahertz column for worst case conditions, when you look at low loss and ultra low loss materials that are likely to be used for Gen 5 designs, we're essentially dealing with between 1.1 dB per inch and 2 dB per inch loss characteristics for these materials at Gen 5 speeds. So that's essentially the parameters that we're dealing with. And again, your specific PCB materials may have different characteristics and properties, but this is a representative example. So with those example loss per inch figures, if you look at a system and try to figure out how far the signal can go on the baseboard based on those characteristics, we end up with an example table like what's shown here. If we look at both the nominal temperature case, the top row, and the worst case temperature and humidity case, the bottom row, we can see that for the different PCB loss material categories, the signal can be routed between 5.5 inches and 12 inches on the baseboard itself. Now, keep in mind that a significant portion of the budget is consumed by the root port package as well as the add-in card. So this distance noted here is simply the distance that can be routed on the baseboard assuming those other components are consuming their full budget. So with 12 inches being technically possible to meet that 36 dB budget, you can see in this example system on the right, which is a 2-socket server, most of these adding card or chem slot routes would fall within that 12-inch budget. But of course, if there are more complex topologies, such as riser cards being used that introduce additional PCB routing and additional connectors, then those more complex topologies would likely fall outside that budget, and some additional form of reach extension would be necessary. So using PCB material is one way to solve the reach problem and to close the budget. Another way to solve that problem is to use active components. There are generally two types of active components in PCI Express systems. One category is called a redriver. This is a mostly analog device that's non-protocol aware and is used to extend the reach of a signal. There's also a retimer, which is a physical layer protocol aware device that's also transparent to system software. And because the retimer actually samples, recovers, and retransmits the signal, this component will segment the PCI Express link into two segments, which can be which can have the full PCI Express loss budget on either side. So it's essentially doubling the reach of a PCI Express channel. Now, to illustrate the difference between a redriver and a retimer, we have these example eye diagrams on the bottom. The bottom left shows an attenuated signal, an eye diagram that's been attenuated by some insertion loss. So you can see increased jitter and vertical closure of the eye. What a redriver would do is it would equalize some of the insertion loss or the ISI due to the insertion loss. But it would not be able to compensate for uncorrelated jitter terms, things like random jitter or uncorrelated deterministic jitter. So the end result would be a slightly more open eye, but you would still have jitter present in the eye due to those uncorrelated jitter sources. A retimer, on the other hand, would effectively sample this eye diagram, recover the ones and zeros, and then retransmit those ones and zeros on a clean clock using essentially a PCI Express compliant transmitter. Looking at some of the more detailed comparisons between the two categories, in terms of equalization capabilities, a retimer being required to meet the PCI Express receiver and transmitter requirements would have a CTLE, continuous time linear equalizer, a DFE, a decision feedback equalizer, and a transmit finite impulse response filter in accordance with the PCI Express spec. Typically only has a CTLE. Another thing to think about is adaptation. So the receiver circuits and the transmitter circuits in a retimer, just like in a root complex or in an endpoint, would be automatically adaptive. The receiver circuits would adapt based on the incoming signal quality, and the transmitter equalization would adapt based on the equalization protocol of PCI Express. A redriver typically has a fixed CTLE setting, which would need to be determined through some extensive experimentation. In terms of diagnostic capabilities, again, because a retimer has a PCI Express compliant receiver, it therefore must comply with the base specification receiver lane margining feature. And so just like any root complex or endpoint, the receiver can be margined to measure the eye diagram, the width, the height, and look at the eye during a link when it's in the L0 state. D-skew is another difference between these two categories of active components. A retimer, again, like a PCI Express component, will perform deskew across all lanes to understand what the skew is and then to compensate for that. Whereas a redriver, being non-protocol aware, would not be able to measure or correct for skew. And then I guess the last thing I would note, summarizing the three remaining rows there, is because a retimer must comply with all the receiver and transmitter specifications, it can be placed in a system effectively in any location where an endpoint could be placed or a root complex could be placed. In other words, as long as you meet the channel requirements of PCI Express on both sides of the retimer, then that retimer is expected to behave like any other endpoint or root complex device in terms of being able to work from a bit error rate perspective and also have the necessary protocol and diagnostic capabilities. On the other hand, redrivers sometimes have placement considerations, meaning they can't be too close or too far away from certain components, and typically that decision needs to be reached through some extensive experimentation and simulation. So when it comes to determining whether a retimer is required in the system or not, there's generally two approaches for this. The one on the left, which I would say is not recommended, is looking at a simple loss budget analysis where you look at your topology, you add up the different loss terms, root port package, non-root package, connectors, system board routing, etc. And if all of that loss exceeds the 36 dB budget, then likely you will need to either make some significant changes or improvements to your topology, or you would need to add a retimer component. The other way, which is more thorough in many respects, is to do a channel compliance analysis using the CSIM tool we talked about earlier to gauge whether your physical channel meets the requirements or not. And that specifically means achieving 15 millivolts I height in the CSIM tool and 0.3 UI width. And if your channel does not meet those requirements, then again, some mitigation steps are necessary, either improving the PCB material quality, shortening the channel, or another option would be adding an active component such as the retimer.
Thanks, Casey. So I'm going to jump in and talk a little bit about clocking considerations and topologies here. When we're talking about clocking, I'm referring to the reference clock, which is the 100 megahertz HCSL clock that's shared among the system elements. So we'll briefly touch on the different clocking modes, the common clock, SRNS, SRIS, and then also look at some of the reference clock considerations on some of the specifications that change from PCIe Gen 4 to Gen 5. So for the clock architecture, this slide is completely from the CHEM perspective. So CHEM 5.0 is going to support both common clock and SRIS and SRNS, which in and of themselves are not new from Gen 4. But it should be noted that SRIS and SRNS are only allowed for bridging to other form factors. So for example, via a riser. For those who aren't aware, common clock is when the reference clock is generated from the host and shared among all the system elements, so they share a common reference clock, whereas SRIS and SRNS are separate reference. So the root port, for example, can have its own reference clock, and the endpoint can have a separately derived reference. The SRNS means that there's no spread spectrum applied to either clock, whereas SRIS has independent spread spectrum, which can be applied either on one side or on both sides. So looking at the table here, for CHEM 5.0 platforms and add-in cards, common clock is the required clocking architecture. So separate reference clock architectures are not CHEM compliant for those particular form factors. What that means is that a CHEM 5.0 compliant host platform is required to supply the reference clock to the connector. And on the opposite side of that, the add-in card is required to use that clock that is supplied, so that enforces a common clock topology among those elements. as Casey showed previously, the riser implementations have the option to choose either common clock or separate reference clock. And that flexibility lets you bridge to a number of other form factors. So in some of those diagrams, we saw 2, 3, 4 connectors in a link, whether that riser card is, for a endpoint that's within a chassis, or you can actually be cabling internally or externally. There are a lot of system considerations that might have you not put that 100 megahertz reference clock on an external cable. So in that case, having that separate reference be part of the spec as an option is why it was set up that way. Now, looking at some of the reference clock considerations and specifications that changed from Gen 4 to Gen 5, one of the, I would say, primary changes is that the jitter limit is reduced. So in Gen 4, that common clock jitter limit was 500 femtoseconds RMS. At Gen 5, that's been reduced down to 150 femtoseconds. It should be noted that this limit is after the PCIe filter function is applied. So if you were to look at different clock sources and buffers in the market, I think almost all that are targeted for PCIe applications are going to give you a jitter specification that does have that filter function applied. So that does help you as opposed to the raw jitter from the clock source. The jitter limit, you should note, includes both the source jitter and the additive jitter of any fan-out buffers between the source and the reference clock receiver. On a motherboard, you might have a 100 megahertz clock generator that has 12 or more outputs. And if you have that number of outputs available and you can fan that out directly, then the only jitter you need to consider is from that single source element. But in an example such as the riser card, where maybe you only get one copy of the reference clock that's going across that connector interface, you might have multiple elements that you want to be common clocked and share that clock. So you're going to add, a 1 to 4 or some higher fan-out buffer, and the additive jitter that that fan-out buffer creates needs to be considered to make sure that the jitter limit is still met at the receiver, at the reference clock receiver. So what we have here is the jitter total can be easily calculated using the root sum square method. So you have the square of the source jitter added to the square of the buffer jitter, and then the square root of that can be considered for the total jitter seen at the receiver. There isn't a specification limit for SRIS, so a common rule of thumb is to reduce the RMS jitter by a factor of √2 or to 106 femtosecond. But again, that's a rule of thumb. That's not a specification that system designers are, need to follow. And one other change to note is that the maximum downspread for the spread spectrum clocking has gone from 5,000 ppm to 3,000 ppm. So any Gen 5 compliant clock generator or I guess clock source that does help implement spread spectrum clocking is going to make sure that it meets those requirements. Now we'll take a quick look here at compliance and interop testing. Both the electrical compliance and interoperability testing and system robustness. Electrical compliance, it could be a full presentation in and of itself, so we'll just look at a few different things that are worth noting that are in discussion for 5.0. So right now, if you go to the review zone, you have both Chem and PHY specifications that are available for review. The Chem specification is currently at version 0.7, and the PHY test spec is at 0.5. So these give a pretty good insight as to where the specification is going towards and some of the components that are under discussion. Here I have just a quick table that shows one portion of that, which is the transmitter compliance specifications and how they've evolved from Gen 3 to Gen 5. As it was shown before, the eye height does not change significantly from Gen 4 to Gen 5. For the system board transmit, we go from 19 to 17.5 millivolts. And for the add-in card, we go from 23 to 22 millivolts. But obviously, the eye width to meet the target bit error rate has reduced significantly from 21 to around 10 picoseconds. And it should be noted that for the add-in card testing for this transmitter compliance, it has to meet the eye limits with at least one transmitter EQ preset. And these limits are, of course, post-receiver equalization as defined in the base spec. There are some tools and available, such as SIGTest Phoenix. The beta version 5.0.15 is available, which has the 5.0 specification compliance test. And vendors for BERTs and scopes are finalizing the test suites to help implement those test specs. These are a few diagrams that we provide the source here in the bottom. So if you take a look at these slides after the presentation, the link should be active. But the Chem preview from October has a number of useful diagrams showing some of these transmitter compliance test implementations. So this shows both the system transmitter and the add-in card transmitter compliance test configurations. As Casey showed previously, the total budget of 36 dB can be broken up to different components. So if you're in the add-in card compliance test, you have 9 dB for the add-in card itself, and then the individual components from the connector and the compliance baseboard all the way to the real-time scope are taken into account to provide that maximum channel. And recall that this path has to have at least one transmitter EQ preset that meets the eye height and width requirements. So a few things to take note that are, I guess, currently under discussion or are changing is that the dual port test is being deprecated for the system transmitter. So what that means is that at Gen 4, both the reference clock and the data have to be connected to the scope, but at Gen 5, only the data is connected. And another interesting topic is possibly using a scope embedding instead of an ISI board. So scope embedding would remove 2 connectors, 1 cable, the ISI board itself from the path, which has obviously the benefit of removing several potential points of failure, along with simplifying the compliance hardware kit. But it does add the embedding capability requirement on the scope itself. So that, again, is still being discussed, and as implemented, if it does go through, they'd work with the vendors to make sure that's implemented correctly. And lastly, the system reference clock test is being explored. So you can look at the PHY test version 0.5 now, and it discusses some of the outlines for what a reference clock test setup and methodology would look like. Right now, there's some TBD on what the actual specifications would be, but more details are expected in version 0.7 of the PHY test. Transitioning now to interoperability testing, what we have here is, I would say, an example methodology for system-level interoperability testing. As folks are implementing these, they'll see that electrical compliance doesn't guarantee system-level interoperation and robustness. So if you take a look at some of the common industry practices, there come out a few categories of interoperability tests that are routinely employed. And what we'll show here in the next few slides is those approximate categories and the states in the LTSM that those types of tests are exercising. So the first test you can look at as a category of link-up repeatability tests. These are simply coming either from a cold boot, so an off state to up the system reaching L0 at the maximum rate and link width, or a warm reboot, from L0 back through detect and through the link states again. And generally, industry practice is to test these different link-up cycles hundreds or thousands of times to gauge the repeatability of normal system operations. So a subset of link partners, depending on the system design, is run through these tests and ensure that all link partners are following through with this full process. Looking at the next group of tests, which can be roughly described as LTSM stress tests, these similarly exercise different paths and different states that might be encountered by the target system. So whether it's secondary bus reset or link enable disable or some of the different power states, these stress tests will again be applied hundreds or thousands of times so that every corner case operation that the system vendor expects is robust. We don't highlight loopback in this group of tests because it's not commonly used in normal link operation, but it's obviously a useful alternate means of measuring the electrical margin. So again, these grouping of tests are more a common industry practice, but they aren't exhaustive or part of any sort of determined compliance. And the last group are some of what we call special use case tests. These are maybe application-specific features, data traffic, and in-system margins. So for example, you have hot plug and unplug, whether that's surprise or managed hot plug. The in-system electrical margin tests, so as Casey mentioned, some of the active components can have in-band receiver lane margining, which is often used to look at the receiver margins and to verify whether they meet the vendor-specific limits. And every receiver within the link, whether it's just a root port and an endpoint, or if there are active devices such as retimers, can be addressed during the L0 state to margin each individual receiver and take a look at the eye diagram. And then lastly, application tests. So these are, again, very specific. So for example, if you had a NIC or a group of NICs and you wanted to measure and validate the throughput, and that would be part of this application test. And that is the, I guess, overall summary of the interoperability testing. And I think we can, Casey, take a look at any questions.
Great.
Okay, thanks, Jonathan.
Thank you, Casey and Jonathan. The first question here is, if a channel passes channel compliance, a transmitter passes transmitter compliance, and a receiver passes receiver compliance, does that guarantee the PCI 5.0 link will operate robustly?
So the PCI Express SIG requires channel compliance, transmitter and receiver compliance as a kind of a minimum requirement. And passing these tests should give the end user some high confidence in being able to achieve that 10 to the minus 12 bit error rate or better. Practically speaking, a lot of people designing systems are seeking to have margin in their system design, either to achieve a lower bit error rate or to have even higher confidence in hitting that 10 to the minus 12 bit error rate. And so that often leads system designers to target a lower channel loss than 36 dB. But of course, you know, the PCI SIG does not provide any specific guidance in that respect.
Great. The next question, any specific changes to the link state power management in the PCI 5.0 specification as compared to previous versions of the specifications?
So I would say not that I'm aware of. Based on my recollection of the spec, I don't think there have been any changes to power management for 5.0. I'm not an expert in that area, to be honest, so I could be wrong about that.
Okay, the next question, how do you know if a link needs pre-coding or not?
Pre-coding, as we mentioned before, is up to the receiver to request the transmitter to enable or disable that feature, and that happens during link training itself. Whether pre-coding is needed or not is largely dependent on the specific receiver implementation. As an example, if a receiver relies heavily upon DFE TAP 1 in its architecture, it may choose to request pre-coding to be enabled during link training because, as we mentioned earlier, when DFE is heavily utilized in equalization, that makes a receiver more prone to burst errors. So each receiver will make its own determination based on its architecture, and then it will request that from the link partner accordingly.
Great. And then how is burst error considered in PCI 5.0 specification?
So that's a good question. Unfortunately, I don't know the answer. I don't know if there's a specific mechanism for burst error reporting that goes above and beyond the normal error reporting mechanisms. I think the general idea is that because this pre-coding circuit is available and negotiable during link training, the receivers in the system need to request that to avoid burst errors. In other words, I think the expected operation of a PCI Express 5.0 link is such that burst errors are expected to not happen, especially since precoding is available. So I don't believe there's any specific error reporting protocols for burst errors.
Okay, great. Next question here is, what system level tools will be used commonly for gauging link performance at PCI 5.0 specification levels?
Jonathan, do you want to take that one?
Sure. So I would say that the PCI SIG doesn't endorse any particular tool, but the base specification does provide for receiver lane margining. So as I mentioned, that allows every receiver in the system, whether it's root complex, retimers, upstream or downstream pseudoport or endpoint, to be margined both in time and voltage. So this allows for measuring the eye width and the height for every receiver in the system while the links are in the normal L0 state. So it can be very useful to use that to gauge link performance for 5.0 systems.
Great. And then I apologize. I'm having internet connectivity issues. So if you all want to continue answering the questions, I'll try reloading.
Okay, I see one other question here posted. Any difference in retimer functionality in 5.0 as compared to 4.0? I think the main differences, just to list them off memory, would be, again, this support for precoding. So a retimer, like any PCI Express receiver and transmitter, needs to support precoding on the transmit side when requested. And in an implementation-specific manner, it may request precoding for the receiver. I think other differences to point out, again, retimer-wise, compared to 4.0, is in 5.0, there's this concept of enhanced link behavior. This is, I believe, an optional requirement for retimers and other components, but if it is supported, then enhanced link behavior allows for things like bypassing equalization to go to the highest rate. So that would allow the link to go from Gen 1 directly to Gen 5. And also it allows for something called no equalization needed, where the link can bypass the equalization states if a receiver supports that. So those are the things that come to mind. Let's see if there are other questions here. Is Gen 1 and Gen 2 supported in the Gen 4, 5, 6 for backwards compatibility? Yes, they are. As with Gen 4, PCI Express Gen 5 does require backwards compatibility, so all the generations are supported in 5.0. Any typical applications where redrivers are preferred over retimers? We didn't discuss this too much on that previous slide, but you can go back and refer to that. I would say, again, in my experience, redrivers are sometimes used in something called a closed system, where the system designer is designing the total end-to-end channel. And there is no expectation that compliant adding card could be plugged in. So if it's a closed system, then sometimes redrivers are used because it's a problem that can be addressed through extensive testing because every component in the system is known. For open systems where you would want to be able to plug in any kind of adding card or multiple different GPUs, multiple different storage devices, etc., then that type of open compatibility generally requires a retimer implementation, which can automatically adapt to the different signal characteristics of those different adding cards. Okay. Here's another question. There's a bunch of questions coming in, actually. Hopefully we can get to most of them here. If not, I think we'll follow up in a subsequent post. Does precoding impact performance? The answer to that is yes. It has a positive impact in the sense that it prevents burst errors. It has a slight negative impact in the sense that the precoding circuit itself will double the bit error rate. So for example, just to pick an example, if the underlying bit error rate of a system was 10 to the minus 13, which meets the PCI Express requirement, by enabling precoding, that bit error rate would translate to 2 times 10 to the minus 13. So it's a slight increase in the underlying bit error rate, with the positive side effect being that you prevent burst errors. Okay, let's see what else. Does PCI SIG provide a tool for interoperability tests? There are some test specifications or test procedures for data link and transaction layer tests, which are typically performed with some kind of an PCI Express exerciser piece of equipment. That test is part of the standard PCI SIG plugfest, and it does attempt to exercise various aspects of the LTSM and various aspects of the protocol. I think that in addition to that, many system designers prefer to perform the tests that Jonathan highlighted, such as cold boot, warm reboot, all the LTSM stress tests, because those would involve their actual components, root complex, and endpoint devices, as opposed to the plugfest test, which are using exercisers that may have slightly different characteristics compared to actual components. Other than keeping the same throughput, does a retimer require to support different link widths for its upstream and downstream ports? So very good question. If you look at the retimer requirements in the base specification, there's a specific description of how the link width negotiation is to be performed. And to summarize it, basically the link width that a retimer will implement is the maximum common width of the upstream pseudoport facing the root complex and the downstream pseudoport facing the endpoint. So as an example, let's say on one side of a retimer you have a by16 root complex, and on the other side of the retimer, again, because this may be a chem slot, you've plugged in a by8 endpoint. The retimer is required to detect this width difference and automatically adjust its active width to by8 to accommodate the largest common width between the two. Another question, if the equalization can be bypassed in retimers in 5.0, then how would an endpoint detect if there is any retimer present? So this is referring to something I mentioned earlier, this enhanced link behavior, which is new in PCI Express 5.0. This, by the way, is not specific to retimers. It's a optional feature that is available to root complexes, retimers, and endpoints. And one of those enhanced link behaviors is no equalization needed. So the question was, if that's used, no equalization needed, how would an endpoint detect if a retimer is present? And the answer is that every system starts off at Gen 1 speed, and the presence of a retimer is communicated to root complex and endpoint at Gen 1 speed through the TS1 and TS2 ordered sets. So before the link even jumps to Gen 5, and before it does this equalization bypass, that information would be exchanged through the training set. Here's another question from our experience at Astera Labs with customers. what are the major system design mistakes and errors with respect to PCI Express implementation in general. I would say, in general, the most common challenges or mistakes, if you will, would be making sure that the system design, the system board, for example, connectors and things like that, are designed to comprehend the fact that those loss characteristics can vary over temperature and humidity. And if the channel is long enough, that variation may push you over the edge in terms of channel compliance. When I'm working with system designers, I often encourage them to consider, worst case conditions, and to make sure that even at those worst case conditions, the physical channel will pass that channel compliance test. Maybe one other thing to add to that, another common challenge or area of difficulty is in analyzing the protocol. We talk a lot about signal integrity here and electrical compliance and things like that. Protocol is another complex aspect to PCI Express. There are many LTSM states, and so having the ability to record and log these different protocol state transitions in every component, root complex, retimer, and endpoint, is critical in terms of diagnosing or debugging link formation issues. So that's one common kind of pain point when people are bringing up a new system, is understanding what went wrong and when, and having that protocol logging capability is, I would say, highly recommended for accelerating those system bring-ups. Okay, any other questions that catch your eye, Jonathan or Megan?
I think we should probably go ahead and wrap up now. Actually, we're coming up upon the hour now, but we wanted to thank you all so much for joining us. These slides will be available on the PCI SIG website, and this recording of this webinar will also be available after we wrap up here. We'll likely also do a follow-up blog as well to post on the PCI SIG website. So thank you, Jonathan, and thank you, Casey, very much.
You're very welcome. Thanks, everyone, for attending.
Yep, thank you.